All right, well, so thanks very much for having me to discuss this paper. It's a wonderful piece. Qihui has written extensively on factor estimation, and this sort of continues in this very nice tradition. So let me give you a little background. So we're sort of trying to estimate latent factors. So if these are excess returns, then neither beta nor F are observed. And somehow we want to learn, well, in this exercise, mainly F. The setting that we're in, even though it's sort of not explicitly stated, but this is an economy that's large. That is, we have many assets. And we also need sort of long time series to estimate quantities like prices of risk well. So the classic papers on latent factors date back 40 years. And they basically said, well, we should look at principal components. And PCA is sort of primarily geared towards explaining variance. And we sort of get dense loadings. That is, all the betas are non-zero. And it's not necessarily geared towards explaining differences in expected returns. And then in the last 10 years, there's somehow been a resurgence in interest in latent factor modeling in finance, which is quite exciting. So this is basically where Connor and Karajcik left us in the 80s. And then a few years ago, Letta and Pelger came along and said, okay, we're going to add this second term here to the PCA objective. And then we're going to consider, in addition to explaining variance, also explaining cross-sectional pricing errors. And depending on how big we choose gamma, that's sort of what we prioritize. And then in principle, you can sort of generalize this idea to sort of add other targets to this, sort of add a bunch of gammas and whatever objective you have in mind. All of these things sort of give us dense solutions, and anything can in principle be a target so long as you have some story to tell on why you want it. And then, this paper comes along, EGS, and they're now basically picking up where other people left off, adding sort of targets. And then they add this sparsity penalty back here, basically enforcing that we're not going to sort of load on all the sorted portfolios or Farmer-Macbeth slopes. And in principle, this approach is incredibly flexible because it nests all these others as a special case. So if you choose gamma 0 and lambda 0, you get standard PCA back. If you choose lambda 0 and put sort of a particular W here, you get RP PCA. And then you can sort of have combinations of those two. So it's quite flexible. You can also build this sparse version of risk premium principal components. And then empirically, the authors sort of take characteristic managed portfolios, apply sparse PCA with this lasso penalty, and then I think the crucial restriction in the estimation is that they impose this sign constraint that we're going to have positive loadings, that we're going to force positive loadings on factors that have positive prices of risk. And then we're going to build, so we're going to have to choose all these tuning parameters to maximize the in-sampler Sharpe ratio. So that's what's going on. Now, if you read the literature, over the last few years, sort of sparsity has taken somewhat of a beating. And so this is AI generated, of course, and for my life, I couldn't explain to ChatGPT that the lasso shouldn't be beating on sparsity. But then at some point, I decided this is a time sink and moved on. So there's been a bunch of papers in economics and finance that have sort of taken issue with sparsity. So there's Giannone and co-authors. Ulrich Müller has a recent paper. And then sort of Gofu, my former colleague, has a paper, and then Nagel and Kozak and Santosh, they've been quite influential. They basically took an explicit stance that if we're working with sorted portfolios as our base assets, we shouldn't sort of look for an SDF that's sparse in those factors. So here sparsity has a big comeback. So this is the figure that Qihui showed. So it's quite interesting. So as we're forcing more zero loadings, explained variance sort of naturally goes down. And then the Sharpe ratio sort of is non-monotonic, but at some point it goes up again. And in many ways, this is something that I would like to understand a little better. So one thing that the authors could embark on is sort of follow an alternative construction. So many years back, sort of Britton-Jones wrote a paper sort of showing how you can estimate tangency portfolio weights just using OLS regression, using this thing. And now, of course, I've rewritten this sort of in the spirit of what the authors are doing as this sort of elastic net regression, where we have sort of a ridge penalty and then also have this sparsity penalty. And it'd be interesting to see if you start from here, will you end up roughly in the same place as you do when you sort of follow the approach that the authors have taken. And in particular, it'd be really interesting to sort of distill out sort of what is how much does sparsity contribute to the party and how much does the sign constraint help us. And sort of the bigger question that's sort of in the back of my mind is sort of how do the authors really think about sparsity? Do we think that the true model is a sparse one, or do we think of this as a way that sort of gives us good approximation properties, even if it's not sort of literally true, possibly? And there's sort of great statistics literature that sort of works on this stuff. And then my second comment is sort of trying to unpack the SDF a little more. So I've taken a snapshot from table 3 in the paper. So this is for 6 factors, the outer sample, time series, and cross-sectional R squared, just comparing EGS and PCA. So the authors do a lot more in the paper, so this is sort of not doing justice to the empirical exercise. But basically, the pattern that we sort of see is that PCA gives you a fairly high time series R square and is sort of beating EGS on that dimension. And cross-sectionally, it's sort of exactly the reverse. And part of this is, of course, by design and exactly what they're trying to achieve. But it sort of makes me wonder a little bit on sort of what's with the rest of the variance. So, we have factors that explain 15% of the time series variance, and they can explain cross-sectional prices, average returns really well. So what's in these other 85%? And so here are some things that is potentially worthwhile exploring. So one thing is this could be truly idiosyncratic risk. So then we shouldn't sort of see any price of risk for this. You can possibly compare sort of the pricing exercise with individual stocks versus factor portfolios to get a little bit at this. There could be a systematic but unpriced component, so people always point to industry factors as sort of the canonical example that, yes, they're risky, but somehow we don't want a premium for it. And then the third thing is that it's sort of priced risk, but it's really hard to distill out. And it would help me, and possibly others, the authors can go a little further in sort of trying to explore this, what's with a missing variance and sort of how we should think about this. And then a sort of a small comment on the data choices in the paper. So the authors start with the Chen and Zimmerman data set, which I think is a great choice because it's sort of open and it sort of helps us connect to other pieces. And then we drop a bunch of characteristics with missing data and a bunch of insignificant characteristics and then a bunch of collinear characteristics. And this sort of then makes it a little harder again to compare to other pieces in the literature. And sort of some questions that are sort of natural to ask that I couldn't find answers to in the paper is, So if we're filtering on t-stats for sample selection, how does this sort of impact subsequent analysis? In principle, when we're doing PCA, we're sort of not super concerned about highly correlated factors. I could imagine that the lasso is struggling a little bit for model selection, but all of these choices may be very well justified, but I think it would help if we can learn a little more about them. So one thing that I think would be an easy exercise is start with sort of very little filtering and sort of show us what's going on. So here are some other thoughts that I think could possibly help the paper. Barillas and Shanken have a very interesting piece where they basically talk about sort of test asset irrelevance, and the idea of that paper is essentially that a set of factors needs to show that it explains sort of another set of factors irrespective of what the test assets are. So one thing that you could do is say, well, okay, I'm going to use my factors and try to explain sort of a competing set of factors and see is there any alpha left. And then you flip the left and the right-hand side and see, do your factors explain potential competitors? And that would, in many ways, be a direct test on whether these factors sort of are better than PC, RP, PC, and those types. Then there is, I think, one of the challenges of this enormous flexibility in this approach is that we need to choose potentially a fair amount of tuning parameters. So we have lambda controlling sparsity, then we have gamma controlling how much we should incorporate sort of many different objectives. And then in principle, we also simultaneously, ideally, need to choose how many factors we want to use to build an SDF. And in many ways, it's sort of not sufficient to move one and see holding the others fixed and seeing what's best. In principle, you sort of want to jointly choose them, and I imagine that could become quite challenging. In sort of other work, I've sort of played with different data generating processes and sort of tried to figure out what gives me sparse versus dense representations. So maybe there's some food for thought there. I imagine the statistical properties of this procedure will be pretty hard, but I have full faith in Qihui. He can figure this out. And then finally, what's sort of a little bit hard in the paper is that we're sort of using different metrics of success. Sometimes we're using sort of R squares, then we're using basically sum of the squared alphas, and it would be interesting to see sort of a more unified treatment for the different applications. Okay, and then there's some minor other stuff that I think I'll tell the authors offline. But in general, I think it's a wonderful piece. I really enjoyed reading it. I think it's a very elegant unification of many different traditions of factor modeling in empirical asset pricing. It sort of brings together latent and observable factors. And on top of that, it sort of resuscitates interpretability, which is quite valuable. I think the sign constraint is intuitive, and out of sample, it works. So I encourage everyone to read this paper and hopefully you'll enjoy it as much as I did. Thank you.